I want to show you a very nice contour integral, which comes from a problem in soliton theory. So it comes from actually a problem that a PhD student has been working on recently. And I'll try and tell you a bit about the background and the motivation where it comes from. But first of all, let me just explain what the specific integral is that I'm going to show you. The problem we want to work out is to evaluate particular definite integral, which is an integral on the whole real axis. And the neatest way to write it is, so it's a complex integral in general, which looks like this. So the problem we're trying to work out is this. Typically, we're going to be interested in the case where k, which you can think of as a wave number, is real valued. And then in case you're not familiar with this thing that's written as sech, or I say sech, the function sech is the hyperbolic secant, so that's the reciprocal of the hyperbolic cosine. So if you wanted to write that explicitly in terms of exponentials, that would be this function. So this is the function that's appearing in that integral, but it's the square of that function. So it's the hyperbolic secant squared. And then if you know about Fourier transforms, then essentially this is the Fourier transform of the function sech-squared. Now, the function sech-squared is a function that's very dear to my heart because it's the solution of a very nice PDE called the Korteweg-de Vries, or KdV equation, which is an equation that describes long waves on a shallow canal. So let me show you a little animation. So I'll tell you about the equation in a minute. I've kind of written the equation called KdV here in a sort of shorthand form. And this is a formula above this thing. U is the height of the shallow water, this quantity, which is a function of x and t. And then actually, if we animate that solution, so it's a humped shape, this is the shape of the function sech-squared, the hyperbolic secant squared. And if I just show you the animation of how it moves, this is what's called a traveling wave. So it just moves with constant speed. Maybe I'll try and slow it down a little bit, just so you can just watch it moving again. So this is a very special kind of wave, which is called a soliton. Okay, so let me go back and explain to you about briefly what a soliton is, and then I'll maybe explain where the origin of this particular problem came from. The PDE that I mentioned just before is called the Korteweg-de Vries equation. Or KdV is how it's normally shortened. So that's a PDE for a quantity U that depends on x and t, in space and time. So one-dimensional space and time. And it looks like, in a kind of scaled form, it's a third-order PDE, but it's nonlinear. So you'll see that the last term that I write is nonlinear because this term here has got the product of u and its first derivative with respect to x. So that's the KdV equation. And it describes, as I already mentioned, if you have shallow water essentially moving in one dimension, so like something like a canal, and we ignore the rest of the extent of the water surface and just measure along the canal. And if you have the surface of shallow water, you can start from what are called the Euler equations, which describe inviscid fluids, so fluids that don't have viscosity or stickiness, which is sort of, to a good approximation, that's a sort of good model for water. And then if you do a kind of approximate or asymptotic solution to describe the motion of the surface of the water on a shallow canal, starting from the Euler equations, then you get this Korteweg-de Vries equation as basically a model equation. Okay, and what's quite remarkable is that this equation can be solved exactly. So in a certain sense, you can find sort of exact solutions to the initial value problem. If you're given a nice initial profile, you can describe how it evolves with time. So there's a whole lot of technology, sort of new techniques that were worked out in the end of the 1960s for solving this special kinds of nonlinear equations called soliton equations. But the important phenomenon that they were trying to explain was a special kind of wave called a soliton. What's special about the KdV equation? Well, in particular, it has this exact traveling wave solution called a soliton. And the formula looks like this. So it's given by this hyperbolic secant squared shape. And then it's got sort of two arbitrary constants in it. So one of them is this parameter kappa, which we can take to be positive, and then x naught is another real parameter, which is describes the position of the soliton at time t equals 0, while kappa tells you the amplitude and the velocity of the soliton. So if you look at this formula, this is an example of what's called a traveling wave, and it has a fixed shape, which is this sech-squared shape, which is this kind of hump shape. And then the height of the wave, or amplitude, which is at the center, is 2 kappa squared. And then this whole profile is moving to the right with a speed which is 4 kappa squared. So the amplitude and the speed are proportional to one another. There's just a factor of 2 between them. And this kind of wave was actually observed first in 1834 by John Scott Russell, who was a Scottish engineer and naval architect. So John Scott Russell, he built ships with Brunel. But something that he did early on, he was working on a canal called the Union, which is now called the Union Canal, on the outskirts of Edinburgh. And he observed what he named the Great Wave of Translation. So on the canal, there was a barge which being pulled along by horses, which stopped suddenly. And it pushed out a hump of water, and then he noticed this hump of water traveling along a canal with a constant speed, and he followed it on horseback for several miles, and he was quite surprised by it because in those days there was no kind of theory which would describe a wave like that. It wasn't described by linear theory. It really needed nonlinear theory, which didn't exist at the time. But he managed to recreate these waves. He built a water tank at home and managed to reproduce these waves and wrote about them. But unfortunately, nobody really paid much attention at the time because they didn't really have a theory that could explain these waves. That didn't come until the end of the 19th century. But what he'd actually observed was one of these solitons, and reproduced their behavior in his own water tank. And he actually made measurements and also found this relationship between the speed and the amplitude. We have essentially this shape wave, this profile, sech-squared. If we forget about time and forget about, just move the wave to be at the origin, and we sort of take x0 to be 0, and then also if we fix the amplitude to be to some constant, for whatever reason, we might want to find the Fourier transform of this profile. So actually the problem that where that arises is another kind of soliton problem. So let me just show you at least a quick flash of where this problem appears. This is a paper by Oxtoby and Barashenkov about what's called a wobbling kink. So a kink is another kind of soliton or a solitary wave. It's a wave that moves, also a wave that moves with a constant speed. And if you look at this equation 1 that appears here, it's another PDE. Now it's a second order PDE. It's actually a relativistic PDE, and it's one of the simplest examples of a relativistic field theory in one space dimension. It's called the phi to the 4th theory. And that has a solution which is a soliton called a kink, which is described by equation 2 here, which is the hyperbolic tangent function. And then this paper by Oxtoby and Barashenkov is about looking at essentially wobbles or oscillations around this kink. So there's what's called phi to the 4th theory. So okay, I won't write it down again. That's a 1+1 dimensional field theory, and the basic kind of solution to that equation is given by hyperbolic tangent, which is called a kink solution. And the kink looks like, shape of the kink is this kind of shape. So it's the tanh function goes between the values phi equals -1 and phi equals +1. Those are the two. That's the two asymptotes of that graph. And then that paper that I just flashed up on the screen is about looking at essentially what's called perturbation theory. So looking at oscillations around this kink solution. Okay. And then it turns out that if you look at this problem about oscillations around the kink, then one of the things that appears is precisely this integral that I started off with. So this is a complex integral with now a wave number k, and in fact a particular value of k that appears in the kink oscillations. And in this paper, they note that you can actually compute this integral explicitly for any value of k. But that's what I'm going to tell you about now, and how you can do that with a nice contour integral. But I admit, when I saw this problem, I thought, okay, well, I'm sure this is a standard integral that must be well known. And so the first place I looked was in what's called the Digital Library of Mathematical Functions. Here, let me show you. So this is the website of the DLMF, the Digital Library of Mathematical Functions, which is maintained by NIST. That's the American National Institute of Standards and Technology. And chapter 4 of this online handbook, it has information about hyperbolic functions, and then there's a section about that which is about integrals with hyperbolic functions. And then lo and behold, if you look down here at 4.40.9, this integral here has got a hyperbolic secant squared. It's written with 1 over Cauchy squared, and there's a scaling. So let me write down that integral. So what the result that they give, so they actually give this result which has a real parameter a. So let me just say something about that. DLMF 4.40.9. They have this formula, and I'll write it with sech instead of 1 over Cauchy squared. So they write it with x over 2, which is just a scaling. And then the answer that they got was, they actually state this formula for a real parameter a between -1 and 1. But actually what we're going to show is that this formula is valid when a is a complex number with a real part between -1 and 1. Okay. And then in particular, if we take the real part of a to be 0, so a is pure imaginary, and we're basically up to a scaling x, we'll get back to the Fourier transform, the Fourier integral that we started off with. Okay. And what about what's wrong with a being 1, or the real part of a being 1 or -1? Well, actually, if you look at this, the right-hand side here, then when a is 1, then you get sine of pi in the denominator, which is 0. Or when a is -1, you get sine of minus pi. So you get a 0 in the denominator, and this integral looks like it blows up. You might say, well, what about when a equals 0? It looks like you've got a problem, you've got a 0. But when a equals 0, actually, this is you have 0 on the top and on the bottom. So this is actually an example where you can use L'Hopital's rule, and you can see that actually this ratio tends to a finite limit when a tends to 0. So the limit there is actually just 4, if you work that out. Okay, so what I'm going to do now is actually calculate this integral by doing a residue calculation. So the idea is that we want to integrate this function around a rectangular contour. So let me just draw a rectangle, and then I'll tell you what the rectangle is. So we've got this function, which is going to be f of our complex variable z, which is going to be e to the az times sech-squared of z over 2. I can also write that as Cauchy squared of z over 2. And then, or maybe you can see, if you know how Cauchy is related to cosine, and you know that cosine vanishes at pi over 2 and minus pi over 2. So in fact, the hyperbolic cosine vanishes at I pi on 2 and minus I pi on 2. So if we take z to be I pi or z to be minus I pi, then this function is going to have poles of those points. Okay, so these 2 points that I'm marking with a cross are where this function is going to have poles, in fact, double poles. And then what I'm going to do is take a rectangle. So there's the vertices of this rectangle in the complex plane, in the z plane. And now what I want to do is do a contour integral around this rectangle. Okay, so we're going to go anti-clockwise, which is the normal orientation that you take for Cauchy's theorem. Okay, Cauchy's residue theorem. Okay, so here's our problem, is to now calculate, if we call this contour gamma or something, then what we're trying to do is calculate the contour integral f of z dz. Okay. So then Cauchy's residue theorem tells us that that's equal to 2 pi I times the sum over the places where f has poles of the residues of f of z. Okay, the sum over the poles. So if we break this down, so this function is an example of what's called a meromorphic function. So it's differentiable everywhere in this in the inside of this rectangle and on the rectangle, except at those 2 points, I pi and minus I pi, where it has poles. And as I said, it has double poles. I'll show you why it's double poles more clearly in a minute, why we can see that. And so, but anyway, if we know that that's the only place where there are poles, then we can say that this integral around this rectangle is going to be 2 pi I times the residue of f of z at z equals I pi, which is first the top pole in that picture, plus the residue at f of z at z equals minus I pi. Okay, so that's the so just to work out this integral, so it seems like I sort of pull this out of a hat, but then you'll see eventually why this is the thing that we want to calculate, and now it's going to give us back at the end the integral that we wanted. Okay, so let me sort of show you some calculations now of, first of all, what this value of this integral is when we do the residue calculation. All right, so let me give you a new screen. So let's do the residue. We've got this function f of z, which is e to the az over Cauchy squared z over 2. What we noticed is that Cauchy of plus or minus I pi on 2 is equal to 0. So hyperbolic cosine has a simple zero at each of those points. That's the same as the fact that the cosine has a simple zero at plus or minus pi over 2. So actually what that means is that the Cauchy squared on the bottom has then a double zero at those points. The numerator is a holomorphic function. Exponential is holomorphic on the whole z plane. So what that means is that this function overall, this f of z, has a double pole at plus or minus I pi on 2. So now what we need to do is calculate the residue. We need to calculate the Laurent expansion of this function around z equals I pi on 2 and z equals minus I pi on 2. Okay. So let's carry on with that. Okay, to do the residue calculation. Well, if you know, so what do we want to do? We want to say, essentially, we can calculate the Taylor series of Cauchy z over 2. We take z equals I pi. That's Cauchy of I pi on 2. And then which we know is 0. So I'm just going to compute the Taylor expansion. So then we would have the derivative of Cauchy, which is shine, and then a factor of half. So we get half, and then times z minus I pi. So I'm really calculating this function around z equals I pi first. Okay, and then, okay, well, what can I say? Well, if you know how, so you know how cos and sine work, then you know how hyperbolic cosine and sine work. So we know that this is 0. And every time we differentiate, we're going to get alternating Cauchy shine. So the next term, when we work out the quadratic term in the Taylor series, that will have a Cauchy. So that would be something with, so I'm just going to sort of say we would have, the next term would have some coefficient, and then Cauchy I pi on 2 times z minus I pi squared, but we know that that's also 0. So actually the next term, the next non-zero term in the Taylor series is going to be the cubic, which is also going to have some other coefficient, but it's not going to matter if I'm different in order of z minus I pi cubed. And then let's try and get this straight. So the pinch of I pi on 2, so that's working out those terms. So now the Taylor series of hyperbolic Cauchy z over 2 around the point z equals I pi is equal to I over 2 times z minus I pi plus something of order z minus I pi cubed. Okay. So now what we want to do is figure out the Laurent series of f of z around that point. Okay. So this is a Taylor series that we just worked out. And now what I want to do is work out a Laurent series of that function of z. Calculate the numerator at z equals I pi. So that's equal to the a to the e to the a pi I And then on the bottom, we've got I over 2 z minus I pi. Okay, so this is going to be, I'm going to write this denominator, which is squared. And then, okay, let's do the Taylor expansion. There's e to the az, so it's the value, and then the derivative is going to be a e to the a pi I z minus this is the Laurent series. Well, now we just want to extract the residue, which is the coefficient of minus 1 power in here. Okay, so this is the residue of the function at pi I, which is the top pole in the top part of the rectangle. And if you just go through almost identical steps, work out the residue at the pole at the bottom of the rectangle, which instead equals minus pi I, then you'll see that it's going to be minus 4a times e to the minus pi. So it's very similar. So overall, now if we just go back to Cauchy's residue theorem, see what it tells us. Where did we come from? It's, we want to take the sum of these two residues and then multiply by 2 pi I. So what that tells us then the integral of this function around the contour gamma that we do around this rectangle is minus 8 pi ai times to the minus 8 pi I, and that's minus 16 pi ai times cos of a pi. And then you might say, what's the good of that? Well, let's go back to the what this integral is. So I'll draw the rectangle. So now I actually want to break down this integral into 4 pieces, which is the integral along the edges of the rectangle. And then we'll see that we actually get back, in the end, we get back the integral that we were interested in at the start. So let me show you that. So let me give them some names. So maybe that's going to be gamma 1, gamma 2, gamma 3, gamma 4. So the idea is that the integral of gamma, 4 integrals. So integrating f along 4 straight lines. And then what are these different pieces? So let's work out the different pieces. So first of all, let's look at the horizontal line, which is gamma 1 and gamma 2. So it's going to end up in 2 integrals with a real parameter that's going to vary from, let's use t actually, so it's pretty clear. So t is going to go from minus r to r. So if you look at gamma 1, then what is this? Well, it's the first thing that we get is f of t minus 2 pi I, and then dz is just dt, okay? And then the integral on the top, gamma 3, but that's going sort of in the opposite direction, going from R, the real part is going down from R to minus R. But that's the same as integrating in the opposite direction, minus that gives you minus f of t plus t pi I dt. Okay, so that's some integral that we have to work out. And let's see what it is. Let's work out what one of them is, f of t minus 2 pi I. Okay, so what is that? Or another way to write that is, okay, so before we simplify that, I just want to look at that. If we have cosh of, let's say z plus or minus I pi, what does that give you? Okay, so to calculate this, we can use the addition formula for the hyperbolic cosine, which is very similar to the one for the ordinary cosine, except that there's a sign, a different plus sign in the middle. So if you do cos of alpha plus beta, you get cos minus sine. And if you do hyperbolic cosine, you get cosh plus sine. So the hyperbolic version. So this will be cosh z cosh of plus or minus I pi. But then, okay, cosh is an even function, so the sign won't make a difference there. And then this is plus shine of z, and then shine of plus or minus I pi. Okay, but then the shine of I pi and minus I pi 0, just because that's I times sine of pi, so it's 0. And then cosh of I pi and minus I pi is equal to -1. So this is equal to minus cosh z. But then if you look in the expression that we're calculating, we've got the square of this here in here in the denominator. So the minus sign will disappear when we take the square. So then what we get is that f of t minus 2 pi I is equal to the minus 2 pi I a e to the at, and then just cosh squared t on 2 in the denominator. And then the expression that we actually want to calculate, we want to subtract off minus f of t plus 2 pi I. So what you can see is that this is going to be, if we put a plus or minus in there, then we get minus or plus. So then finally the integral that we wanted to calculate along the two horizontal contours, the horizontal parts of the contour. So we get integral of gamma 1 z plus integral gamma 3 and z. Now what we get is an integral along the t-axis, the real t is the real diameter, and we have e to the minus 2 pi I a minus e to the plus 2 pi I a e to the at divided by cosh squared to c. So now if you stare at this, you see that there's a factor in front, which we can simplify. This part in brackets here we can write that in terms of sine. So what we get is finally is minus 2i sine 2πa, and then we have the integral from minus r to r of e to the at sech-squared t over 2 dt. So you see I've replaced the Cauchy squared in the denominator with that sech-squared. So now you can see that this is actually the integral that we're trying to calculate if we take the limit when r goes to infinity. So in the limit, we sort of can say it's a conclusion. The limit when r tends to infinity of the sum of these two horizontal integrals is equal to that times the integral. So this limit up to this factor of the sign in the front is exactly the integral that we want to evaluate. Okay. So what can we say? Well, we know that this we know what the integral is around the whole rectangle. So we've looked at the horizontal parts, and now what we need to do is have a look at the vertical parts. And I'll leave part of this as an exercise for you to check. But we want to look at these integrals along gamma 2 and gamma 4, so the vertical contours. So that's going from r minus 2 pi I to r plus 2 pi I here, and from minus r minus 2 pi I to minus r plus 2 pi here. So the integral along gamma 2 f of z to z plus the integral along gamma 4 z to z. So now I'm going to introduce along gamma 2, I can take a real parameter s, let's say, which is going to run from minus 2 pi up to 2 pi. So we'll have an integral from minus 2 pi to 2 pi of f of r plus is. Okay, so if I take what I've done here is I've taken z to be r plus is. So then that gives me, just to be clear, so what does that give me? That gives me dz is I ds. Okay, so then this will become, so I can just add that. There's I ds. And then now if you look at the integral along gamma 4, so let me just flip back a minute to that picture. Gamma 4 is a contour going down, part of the contour that goes downwards, but we can just do the integral going upwards with a minus sign. So, okay, so what we get is the same kind of integral. We can write that as minus the integral from minus 2 pi to 2 pi. And then it'll be f of minus r plus is times I ds. Okay. Okay, so I wouldn't go through the steps of the second substitution, but it's almost identical to the first one that we did with gamma 2. So let's just have a look at this 1, which is the integral along that from the integral on gamma 2 up to a factor of I, which is not important. What I want to show, in fact, is that this integral here and also this other integral for gamma 4 both tend to 0 as R tends to infinity. So let's write this out. It's the integral from minus 2 pi to pi. Okay. So what I want to show is that that this tends to 0 when R goes to infinity. And the way that we're going to do that is by having a look at the hyperbolic cosine in the denominator. But this is actually where we need the assumption that we mentioned at the start, which is that the real part of the parameter A lies between -1 and 1. Or another way of saying that is that the modulus of the real part of A is less than 1. Okay. So far we haven't used that assumption at all. Okay, so we could use the addition formula for Cauchy, but actually some ways we can just not worry too much about that and just write down explicit formula with exponentials. So let's look at this hyperbolic cosine. It's 1/2 of e to the r plus is over 2 plus e to the minus r minus is over 2. Okay. And then in a very precise sense, this grows like 1/2 e to the r over 2 e to the is over 2 as r tends to infinity. So this symbol here is the asymptotic symbol, this twiddle symbol, tilde symbol. What it means is that the ratio of these two quantities tends to 1. Okay, so if we're looking for large R, then the e to the minus r on 2 doesn't really play any significant role. So then if we look at the integrand here, then we see that e to the AR, e to the IAS over Cauchy squared. So, okay, so this ratio, which is the thing just in this integrand here above, what can we say about this function? So, well, this for large R, this is like e to the AR, e to the IAS divided by, and then this will be 1/2 e to the r over 2 e to the is over 2 squared, which is 4. And then I'm going to write this as e to the power of a minus 1 r, and then e to the IAS plus minus is. Okay, so if a was real, this thing would be pure. This other term would be complex number of modulus 1. But anyway, it's just some fixed complex number. What we're interested in is for fixed s, that's a fixed complex number. What we're interested in is what happens when r tends to infinity. And the point is that if a has a real part between -1 and 1, then the real part of this thing, a minus 1, is negative. Okay, so what I'm saying is that if the real part of A is between -1 and 1, and that implies that the real part of A minus 1 is negative. So that tells you that this whole thing tends to 0. So e to the AR plus IAS over Cauchy squared R plus IAS over 2 tends to 0 as R tends to infinity. So that basically tells you you've got an integral that depends on R, and the integrand tends to 0 as you take R to infinity. So that tells you that the whole integral is going to tend to 0. So what you can say then is that I have these two integrals. I have the integral, this is basically up to a factor of I is the integral okay, so that we've just shown that that tends to 0, and similarly we take the integral along gamma 4 of f, then that also tends to 0 as R tends to infinity. Okay, so now what do we have at the end of the day? Now we can work out the answer that we wanted. Okay, so what we've shown is that this integral around the contour gamma is equal to, and also we know that from the residue calculation, so we can put in the residue calculation, and the residue calculation gave us -16 pi AI cos A pi. Okay, so this is, so this whole thing is equal to -16 pi AI cos of A pi, the sum of all these things. But now what we've just shown in the limit, when the rectangle gets longer and longer with a fixed width, this tends to 0, this tends to 0. These two parts we just worked out, they tend to a multiple of the integral that we wanted to calculate. Sorry, I'm going to put brackets on it. So what was that? Let's just copy it down again. So going back to here, yeah, we got -2i sine 2 pi a. So this is -2 pi sine of 2a pi times the integral that we want to work out. Okay, so then when we've taken the limit, we compare those two things, what we get is that -2i sine 2a pi times the integral that we're interested in is -16 pi I times cos A pi, and then we can well, we can cancel a few things. So we can cancel the i's on both sides. We can cancel the minus signs. So we can write I. But yeah, then with double angle formula, that gives us. So then now you can see that also these cosines cancel. And then there's another factor of 2 that cancels. So finally the answer we get The integral that we had was the integral on the whole real axis of e to the at and then sech-squared TL2 t, and that's equal to 4a pi over sine of a pi. So that's the integral in the form that it was given in the digital library of mathematical functions. And now finally, if we want to get the Fourier transform integral, so we can take t equals 2x, and we can take a to be I times a over 2. And we can take, well, so this formula that we just calculated from the contour integral is valid when the real part of a is between minus and 1. But in particular, we can take s of a Fourier integral. So a times t is just gives us e to the I x. And then we have sech-squared x, and then dt is going to be 2 dx, and that's got to be equal to so that's 2 pi k pi divided by sine of ik pi over 2. You've now got a factor of 2 on both sides. It cancels. So finally we get the answer that we started off with, which is the Fourier transform of the soliton profile, sech-squared profile. And then we can sort of simplify this a little bit, because on the right hand side we've got sine of an imaginary quantity with an I on the bottom. And if you know about the relationship between sine and hyperbolic sine, then you can just see that actually you can write this in terms of hyperbolic sine. So that's what we'll do. So finally, we can write this as sech-squared of x dx is equal to, it'll just be k pi divided by hyperbolic sine, or sinh, shine. Different people say it different ways. I like to say shine. So that's the answer. And this is a real valued integral for real k. And actually that's sort of easy to see that actually the real part of this integral on the left is, so a priori this is, as I said, this is a complex integral because e to the ikx is complex, but the real part gives you cos kx sech-squared, which is an even function, so that's a real thing. And then the imaginary part gives you sine kx times sech-squared, which is an odd function, so that gives you 0. So the imaginary part of this Fourier integral is 0, and so in fact the right hand side is a real function of k. Okay, so that's what I wanted to show.